So Euler's theorem told us that a graph is Eulerian precisely when, assuming that the graph is connected, each vertex has even degree. Using this fact, I'm asking you to prove that a connected graph is Eulerian if and only if you can split the edges into cycles so that no two cycles have an edge in common. They might have vertices in common, but no edges in common. It is much easier to prove this using the degree condition. So instead of proving that this cycle condition is equivalent to being Eulerian, prove that this cycle condition is equivalent to the even degree condition. That is a hint for this exercise that I'm leaving to you. On a related theme, you can ask, okay, now we know when a graph is Eulerian, when is a graph semi-Eulerian? So when do you have an Euler trail that is not necessarily closed? And the proposition is that a connected graph is semi-Eulerian if and only if all vertices except precisely two have even degree. So, for example, you might have a graph like this. And here you have two vertices of odd degree and the remaining vertices have even degree. So your Euler trail will have to start in one of the odd degree vertices and end in the other odd degree vertex. And apart from that, it will behave exactly like a closed Euler trail, so it will need even degrees because it will enter and leave all other vertices. One way to see why this is true, I will not give you the full proof, is, well, what can I do with such a graph? Look at these two odd odd degree vertices and draw an extra edge between them. Now all vertices have even degree, and if you include this edge, you get a closed Euler trail. So if you remove this edge, you will get a non-closed Euler trail. So far, we have looked at this as just a fact. So can we or can we not find an Euler trail? The proof, unfortunately, as we saw, while it was very powerful and relatively short for a theorem of this caliber, it was not constructive, meaning that it did not give us an algorithm to produce an actual Euler trail. It used the induction hypothesis, assuming the smaller graphs were already dealt with, so to speak. So is there an algorithm to produce such an Euler trail if you know that a graph is Eulerian? The answer is yes, and one such algorithm is Fleury's algorithm. So what does Fleury tell you? He tells you the following. If you take an Eulerian graph and follow these simple steps, you will produce an Euler trail. So what are the steps? You start at any vertex you want, and you walk along the edges. Okay? But you don't walk randomly. As you walk, you delete every edge you have walked on and delete all the possible isolated vertices that might have become isolated when you have deleted these edges. In more violent terms, you walk in a city along the bridges or streets, and each time you pass a street, you blow it up. And if ever there is a house that now no longer has any streets leading to it because you blew up all the streets, well, you might just as well blow up the house too. The only condition you have to always follow when you are doing this walk is that you only use a bridge if this is your only alternative. So remember, a bridge is an edge such that if you remove this edge, it disconnects the graph. And indeed, this third condition, the third part, is exactly what keeps the bad thing from happening. So what is the bad thing? The bad thing is that you cut yourself away from the starting vertex. So let me explain how this works. So assume you started in a vertex U, and after some walking, you came to a vertex V. Now, what you don't want to happen is that you take a bridge that will lead you to a component that doesn't contain U. Then you will never be able to get back to U. But so we have to somehow show that this will never happen. So we have to show that at each point, you only have at most one bridge, and that would be the bridge that would lead you back to civilization, back to you, where you started. Because if you had another bridge, so assume you come to the vertex V, and you have, among all the edges you can take, you have more than one bridge, and then one of these bridges leads you away from your starting point and into a different component. Well, it's not a component yet, but once you go to W from V and delete this edge, you will find yourself in a component disjoint from that of U. But if that happened, then since before deleting this edge, the vertex W had an even degree, now the vertex W had an odd degree. So in this component, there will be exactly one vertex with odd degree, because all other vertices have even degree, because the graph is Eulerian. But this violates the handshake lemma, because then the sum of degrees is not even. So this cannot happen, meaning that if ever you are in a situation where your only choice is to take a bridge, there will only be one bridge, and that will be the bridge that leads you back to the component of U. I made this reasoning for the case where V is different from U. There is similar reasoning for V equals U, but without delving too much into the details, this gives you the general idea. And writing this in the form of a sketch of a proof, step 3 ensures that step 2 never brings you to a disconnected set, because you would have something that violates the handshake lemma. Also, the same step will ensure that when you arrive into U and there are no other edges into U, that means that there are no other edges at all. So altogether, this algorithm produces your Euler trail. If you're interested in going through the details of the proof, you can find them in the book or in the notes. So let's look at an example of how Fleury's algorithm works. This is an Euler graph. You can check that the degrees are even. And now let's try to find an Euler cycle that starts and ends at this vertex U. If you'd like, you can stop the video here and do this on your own and then see how I will do it. There are many possibilities. So remember, our only rule is that we never walk along a bridge unless we have to. So starting with U, I'm going to choose to go down this vertex, this edge, sorry. Then I go up diagonally. Then I go back here. Now here, this is a bridge, but I have no other choice. So I will go here. And once I've done that, I delete this vertex as well. From here, I go down here. Now again, I have a bridge, but I have no other choice. So I go into here and delete this vertex. From here, again, I have no choice. Now here I have several choices. For fun, let's go straight up. Now here I have two choices. I could go left, but this is a bridge, and this would leave me in a bad shape, but I cannot go across bridges if I have a choice. So I will make my choice and go down here. And then the rest is pretty obvious because there are no choices at all. And I come back to my U and there is nothing else. So this is Fleury's algorithm. So far we've dealt with graphs that are not directed. You can define what it means to be Eulerian even for a digraph. And the definition is a natural one. So you call a connected digraph d-Eulerian if there is a closed, now directed trail that includes all the arcs of your graph. If that does not happen, but you have a non-closed such trail, then you call your graph semi-Eulerian. So a necessary condition for this to be possible at all is that your graph is strongly connected. Because if you have an Euler trail, then you will get a path between any two vertices you choose, because your graph is connected, so all vertices will be visited automatically. So then there will exist a directed path between any two vertices, so the graph is by definition strongly connected. On a related note, if you start with an undirected graph that is Eulerian in the sense of undirected graphs, then that graph is orientable, meaning that you can put arrows in on the edges so that the digraph becomes strongly connected. And why is that? Well, just follow your Euler trail and put arrows in the direction of the Euler trail. This will give you an Eulerian strongly connected digraph. And there is a similar theorem to Euler's for digraphs, and it says the analogous thing, which in this sense is that a strongly connected digraph is Eulerian if and only if the in degree of each vertex is equal to the out degree. Again, in my personal taste, this is even easier to understand than the undirected version, because here you know that at each vertex you will go out as many times as you go in, so that guarantees that you will have your trail. This is for strongly connected digraphs, as we saw earlier in this page. If the graph is not strongly connected, it will not be possible to have an Euler trail.